Hi, welcome to another edition of Holyfield Physics TV. Today we're going to look at the motion of charged particles in electric and magnetic fields. This is for the OCR Physics A2 course, Fields, Particles and Frontiers of Physics. So let's look at the motion in a uniform electric field. Here we have a positively charged particle entering the field with a velocity to the right, and the force acting on it, the electric force acting on it, is upwards. And that force is equal to the field strength E times charge Q. Now field strength is V over D, so we have the force is VQ over D, D the separation of the plates. We have the horizontal velocity staying constant, but also the electric force stays constant. So our particle moves upwards as it moves to the right. And it follows a parabolic path. This is because the force is constant and is always in the same direction, and it's exactly the same as projectiles in gravitational fields. Now if we look at the motion in a B field, in a magnetic field, here we have a B field into the paper, into the screen, and again we have a positively charged particle. So it's moving to the right, so our current is to the right. And using Fleming's left-hand rule, this gives us direction of force, direction of motion upwards. Particle moves on, but notice that the current has changed direction, so we have to change the direction of Fleming's left-hand rule. And again moves further, and again the direction of current has changed, and so the direction of the force continually changes. And the magnetic force is always perpendicular to the motion, and so we end up with circular motion. In other words, the magnetic force acting on this charged particle is a centripetal force, and we have circular motion. So, electric field, parabolic, magnetic field, circular. But what's going to happen to the motion of the particle if the two fields are combined, if we have an electric field and a magnetic field? So here's our electric field between two plates. It's downwards, direction of the field, and we have a magnetic field into the board. Here's our negatively charged particle. It enters the combined field. Because it's negative, conventional current is to the left, and using Fleming's left-hand rule, that gives us a magnetic force downwards in this case. The electric force, because it's a negatively charged particle, is upwards. So if we have the electric force greater than the magnetic force, the particle will move upwards as it moves to the right. If we look at a different scenario, same negatively charged particle, but this time the magnetic force is greater, the resultant force on the particle is downwards. So our particle follows a downward path. The final possibility is again with our negative particle. We have the electric force and the magnetic force equal and opposite to each other. In this case, there's no resultant force, and so the particle is undeflected. It carries straight on through. And here are the paths being traced out. So we have equal forces, gives us an undeflected path. If the electric force is greater than the magnetic force, in this case the particle will move upwards, and if the electric force is less than the magnetic force, in this case the particle will move downwards. So a particle of charge Q enters a combined E and B field with a velocity v. This time we're going to take both the magnetic force and the electric force to be equal and opposite. So we have F equals BQV, FE equals EQ. That gives us BQV equals EQ. The magnetic force and the electric force are equal. And if we rearrange that, we have the velocity of the particle is equal to E over B, the ratio of the electric field strength and the magnetic flux density. Notice, the charge is unimportant. It doesn't matter whether it's a positive charge or a negative charge or the magnitude of the charge. The only thing that is important in this case is the velocity. You've been watching Holyfield Physics TV. My name's Richard Gould. Thanks a lot for watching and listening. Work hard, do well in your exams.